So we are now going to start the second section of this chapter, and this section is about point set topology of metric spaces. And we are going to start our discussion with the notion of a metric ball, which are also simply called balls. So this is the definition 12 to 1 of a ball in a metric space. So let x comma d be a metric space in which we have chosen a point x naught and say R is a positive real number. Then the ball in X centered at x naught with radius that positive real number R in the metric D is defined to be this set. We are coming to the notation afterwards. Let us first see what the set is. It is the set of those points x in the space such that the distance between x and x naught is less than R. So you can clearly see that this notion of balls is motivated by your usual open disk that you have in two-dimensional plane. Say you think of your plane where you have chosen a geometric point like this one, and you are also thinking of a positive real number R. For the sake of specificity, suppose that R is 1, okay. Then you can consider the interior of the circles whose center is your chosen point and whose radius is R. So that will be your open disk with unit radius. It is like that. The only difference is that, well, I should not say difference, but it is more general. It's in a general metric space. And we are using the metric to measure distance, whereas in the plane we use our usual Euclidean distance. And regarding this notation, you can see that B, you can see B here, B stands for ball. You can see the center here, comma, the radius. And also the metric space has been mentioned so that we can understand where we are considering this ball. But often, if this metric space is already understood, we drop it from the notation and we write the more simple notation like that. This one, B of x naught comma R. So let us next see a few examples of some concrete metric spaces and balls in them. So in this example, we are considering the metric space, which is what I said just now. That is, we are going to the source of this definition. This is our usual plane, and the metric is also our usual distance measuring metric that we always use when we study ordinary plane geometry. In this metric space, that means in the literal plane, the ball in it with center 0, 0 and having radius 1 is this. So you can see that it will just be the set of those points in the plane whose distance from the origin is less than 1 for each one of them. And what is that distance? You know the Euclidean distance of any point x, y from the origin. It is square root of x square plus y square. That should be less than 1. But that being less than 1 is equivalent to having x square plus y square less than 1, because x square plus y square is a non-negative real number. That is why. And that's why you can clearly see that this ball is just your unit disk in the plane whose center is at the origin. So that means it's the interior of, interior means normally what you know as interior, it's the inside of your usual unit circle that you also consider when studying trigonometry. But we are going to consider other metrics on R2 as well. So let's see. If we instead consider the metric DL1, the taxicab metric on R2, and consider the same ball, well, not exactly the same ball because the metric has changed, but that same ball in the sense that the center is still the origin and the radius is 1. Then this is what you get as that ball. It's the set of those points in the plane whose distances from the origin are all less than 1, but this time taxicab distance. So what is the taxicab distance of this point from 0, 0? Mod x minus 0 plus mod y minus 0. That means this. That should be less than 1. So here geometrically also the region changes. It is no longer the interior of a circle, but the interior of a diamond shaped region. I ask you to graph this and see for yourself what region you get. And next we are also going to consider the discrete metric on R2, and let's see what happens to the ball. In the discrete metric, that corresponding ball becomes the singleton set consisting of the origin only. But why? Can there be anything? Okay, let us forget about other points. Let us first see how the origin itself is inside the ball. What is the distance of the origin from itself? 0, regardless of the metric. It's a discrete metric, fine, but that's always the case with any metric. The distance between a point and itself is equal to 0, and 0 obviously is less than 1. So at least the center is lying inside this ball. Can we have any other point in R2 which also lies in this ball? If you take any other point in R2, then its discrete distance measured by the discrete metric from the point 0, 0 is equal to 1, because that's the definition of the discrete metric. So that obviously is not less than 1, it is equal to 1. So no point other than this origin can lie inside this ball. So in this very peculiar case, the ball is this single point in the plane. However, another extreme is this. Say you take the radius to be not equal to 1, but a real number greater than 1, and then consider the ball in the discrete space with the origin as the center and that r as the radius. This time, however, the ball becomes the entire plane. Why? Well, as we have already seen with this case, 0, 0 will lie inside the ball always. But what about the other points? Any other point you take in the plane, its discrete distance from the point 0, 0 is equal to 1, and 1 is less than r. So by the definition of this ball, that any other point will also lie inside this ball. So everything lies inside this ball. In other words, this ball is the entire plane. So it's an extreme case. Either the ball is a single point or the entire space. In this next example, we consider the metric space of the set of all real numbers with the usual metric D. In it, the ball centered at the real number 5 and having radius 2 is the open interval 3, 7. You can see in this figure why that is the case. 5 is the center, and we want those real numbers which are at a distance from 5 less than 2. So it cannot be 7, because the 7 is 2 units away from 5, and so is 3. Okay, so 3 is also not a point in this ball, and neither are the points on this side of 7 or on that side of 3. But all points which are lying between 3 and 7 exclusive, they are having distances from 5 which are all less than 2. So this is this ball. So you can see that although the moment we hear the word ball, a 3D figure comes in our mind. But depending on what the metric space is, if we can even think of something visually, depending on what the metric space is, the ball actually changes. The concept remains the same, but it looks different in different types of spaces. And we then have this remark also, which is just a general thing which you can clearly understand. The smaller the radius r is, the smaller this ball is going to be. In some sense, we cannot make it precise. Okay, it's just that if you make the radius smaller, then the condition for the points in the metric space to be inside this ball has become more stringent, more restricted, that their distances from the center, they have to now be smaller for that smaller r. But we note this thing which we also saw in that example, that the center is always inside the ball. That is because the distance of the center from itself is equal to 0, and there is something else also. And because r is greater than 0, that is why. Because we have defined balls only with positive real radius. We do not consider balls with 0 radius or negative radius, because if we similarly define such balls, they are always going to be empty. So there is no point even considering them in the definition. And next week we are going to use this notion of metric balls to take subsets of metric spaces and then define interior points, exterior points and boundary points in the metric space with respect to that subset. It's something you will find very natural and very interesting also. So see you next week with those new things. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.